All right, welcome back to EDU 8304. I want to start today with the discussion of assumptions. And I pose a question here, what are they and why should I care? So hopefully by the end of this PowerPoint, you'll have a little bit of understanding about both of those. I try to throw in a little humor sometimes because I know stats can be kind of boring to some people. So this little guy here says, of course, we have to begin with certain assumptions. Let's assume I'm right and you're wrong. Anybody else feel like that sometimes at work? Well, let me start by saying these assumptions are different from our research design assumptions. So whenever we're developing a study, we're getting our proposal together, doing all that reading, that background, that gathering of information, and we decide what we're going to do and how we're going to do it, we have some assumptions about our study. Things like participants will respond honestly, the sample will be obtainable or reachable, those types of things. So those are research design assumptions. The assumptions I'm talking about here are tied to each analysis. So whenever a certain analysis is developed, it's developed under certain conditions of the data. And by that I mean these analyses. So think about the ones we've talked about so far. The z-test, the one sample t-test, the dependent samples t-test, the independent samples t-test, and then the ANOVA. Those are the 5 we've talked about so far. Whenever we run those analyses, assumptions are conditions the data needs to meet in order for us to trust the results of the analyses. Because when the analysis, say ANOVA, when ANOVA was developed, it was developed and it works correctly if your data looks a certain way, or if your data has meets certain characteristics or certain conditions. If your data meets those conditions, then you can trust the results of the ANOVA. And so those conditions, we're calling those assumptions. Okay? So like it says here, assumptions are characteristics data should possess if parametric analyses are to be conducted and you plan to have results that can be trusted. Okay? Parametric analyses are just the ones we've talked about so far. Those are analyses that happen with intervally scaled data. There are some analyses you can do when you have, say, only categories, like maybe you have a big data set, but it's all categories, like yes, no, right, wrong, demographic categories. Well, you can still analyze that data, but it's not with these parametric analyses, okay? They're called non-parametric. So for us, if we want to be able to trust the results of our analyses, we've got to check our data first, okay? So there are some general assumptions, okay? Like I said, the assumptions must be checked prior to running the parametric analysis or the analyses we're going to talk about in this course. They don't apply to nominal or categorical variables, so these only apply to those outcome variables. So say you were running an ANOVA. Remember, an ANOVA compares groups on one outcome. Okay, so say you were comparing males and females on frequency of toilet cleaning in a month. All right. Well, males and females, we don't have to check assumptions on that because those are categories. But the frequency of toilet cleaning, we do need to check the assumptions of that data. Okay, and that's what this second bullet is talking about. It doesn't apply to categorical data. All right. These are not checked for doing simple things like calculating the mean, the median, the mode, standard deviation, and so on. They're only checked before running an analysis like an ANOVA or a t-test or the other ones we'll talk about this semester. The 4 assumptions we're going to go through here are very general. But as we talk about the different analyses this semester, we may add to this list of 4. We may take away from this list of 4. And it might look, and it will look, different for each analysis. But if we start and build the foundation based on these 4, then it'll be a little easier to add and take away as we go along. Okay, so there are 4, like I said. The first 2, they're, as far as doing something, there's not really much to do. We just need to evaluate our data. So the first assumption says interval data. In order to conduct a parametric analysis, the dependent variable must be at least intervally scaled. Okay, so think about those outcome variables. That's your dependent variable. A STAR score, a depression inventory score, a self-efficacy score, some sort of interest inventory, any type of a leadership questionnaire, leadership style questionnaire, any type of outcome you're interested in, that's your dependent variable. And your dependent variable has to be measured at an interval level or ratio. And remember, interval variables are our scores, our scored score. Remember, interval like a ruler, we have to have equal intervals between the score possibilities. So like percentages on an exam, those are equal interval, because the difference between an 80 and a 90 is equal to the difference between a 90 and a 100. See what I mean? They're equal interval. Okay, so whatever that outcome is, maybe you are looking at a self-efficacy measure of first-year teachers. Well, that self-efficacy measure you select needs to be scored at an interval level. Okay? The second one is what we call independence of observation. And this assumption says data from different participants does not influence other participants' data. So, for example, when you were administering the self-efficacy instrument to your first-year teachers, they were not working together. They were not sitting together in a group. They didn't feel peer pressure to answer a certain way. They weren't allowed to copy off someone's paper, those type of things. And in addition to that, you don't have, if you're comparing groups, you don't have participants in multiple groups, okay? So the data is independence of observation. Now these two, we don't, like I said, we don't have anything to physically do, but we as the researchers know if our data meets this. I mean, I know if that self-efficacy instrument I selected, I know if it's intervally scaled or not, and I know how I administered that instrument and how that data was collected. So I can tell you if there's independence of observation and if it's interval data, but there's not anything I need to do to my data set. Now, if you're thinking about a large-scale data set, you'll have to explain to the reader how that data was collected so that they'll know you've met independence of observation. All right, and we're going to go through these here, and then we're going to practice them, and then we'll look at some write-ups, because even if we understand the assumptions and how to check them, it can be a little tricky when we start to put it into paragraph form. Quantitative writing, quantitative reports, on the good side, it's very formulaic. So once you have it down, it's going to become really repetitive, and that's a good thing. But on the downside, it's kind of hard to get the verbiage at first when you first start writing it. But we're going to do it over and over and over again. You'll be fine. It's just going to take a little bit of time. So let's just concentrate on how to check them, and then we'll worry about how to write it up. Okay? Now this one, normally distributed data. Okay, so remember that normal distribution we talked about last semester? We have to assume, in order for our, let's say we're doing an ANOVA, in order for the ANOVA, the analysis of variance, to operate properly, our data has to be normally distributed. And again, it's just our outcome variable. So that self-efficacy variable, those values have to be normally distributed. So I'm going to check for a normal distribution. Now, we have many ways we can check for a normal distribution, and we'll go through the different possibilities in a different video. But just know for now that we can check our PP plot. We can also check a QQ plot, which is similar. So the plots are a little more subjective, and we'll look at those on SPSS here in a minute. The KS test is available to you, and you can also look at skewness and kurtosis values. And what I talked about in class was, it's good to know how to do all of these, but you really only have to check one way. And so what I usually do with students is take them through 4 different ways, or actually 5 different ways to check if they have normally distributed data. And students typically kind of gravitate toward one method or another, and then that's the one you use for the remainder of the semester. You don't have to do all 4 or 5 of the checks. You just kind of pick out one that you like and that you find doable and trustworthy, and then go with that. All right, so we'll do some examples of these shortly. The last one is this idea of homogeneity of variance. So variance of the outcome variable should be consistent at all levels of the independent variable. Okay, we're going to evaluate this with Levene's test, and we actually want this result to be non-significant because we want to fail to reject the null. The null is going to say the variances are all equal. Okay, so look at the name of this assumption. It's called homogeneity of variance. And we know what homogeneous means. It means the same, right? So we want that variance to be the same for each of our groups. All right, I'll draw a little example of this in the next video to try to explain exactly what's going on here, and then we'll evaluate it with Levene's test. All right, so what do you do if you fail these assumptions? Because remember, the assumptions are there, and our data has to meet the assumptions in order for us to trust the results of our analyses. So, man, I've spent months on my dissertation collecting this data, and now that I'm checking the assumptions, oh, I'm so upset that my data is failing the assumptions. So what that means is I really should not proceed. So what happens to my dissertation? Do I just have to quit or start over, or what? Well, if your data fails 1 or 2 or 3 assumptions, we have some methods we can use to kind of help that. We can first check your data for outliers. If we have a legitimate reason, we can remove the case. Anytime you remove the case or remove the piece of data that you feel like is causing you to fail an assumption, you have to provide a rationale to your reader. It's not ethical just to remove the case and not report it and go on with your study. We always want to report what we removed and why. I can give you an example. I had a student working on her dissertation. Her data was failing several assumptions, and we took a look at it, and she was using pre-test, post-test data, and one of her students' score on the post-test went down dramatically. I mean, just crazy different. So say maybe he had a 90 on the pre-test, he went down to something like a 10 on the post-test. I mean, it was just incredible. And that piece of data was an outlier because all her other participants went up 3, 4, 5, sometimes even 10 points on this pre to post test she was giving. So when she investigated that particular participant, she found out that on the day of the post test, he did not take his ADHD medication. And this is a child who was severely influenced by ADHD, and his executive functions were very much inhibited whenever he was not on his medication. So because she had a rationale and because she reported it, she went ahead and removed that outlier, and when she did, her data met the assumptions. So in cases like that, it's perfectly reasonable to remove the case as long as you report it. Other options include transforming the data, or changing the score, or you might have some missing data, and we have some methods for estimating those missing values. So transforming the data and changing the score, those are kind of outside the scope of this course, but I did just want you to know that in real life, for your real study, if your data fail those assumptions, all is not lost. There are things that we can do to, and do so ethically, to help you meet those assumptions so that you can proceed with whatever data analysis you want to do. Okay, so the next thing we'll do is pull up SPSS and go through a check of each of these assumptions to show you what it looks like as you compute it on SPSS. So again, just a little silly cartoon. I like to think of assumptions as like going to the dentist. It's not super fun, but if you don't do it, it can be a lot more painful later. The worst thing is to submit your work for publication and have the reviewers come back and just trash your paper because you didn't check the assumptions. Okay, so it's something that every researcher should do. It's something that you should be on the lookout for as you're reading journal articles. The writer may not go through lots and lots of detail about how they check the assumptions, but the writer should at minimum, mention the assumptions, mention that they were checked, and that the data met the assumptions or didn't meet the assumptions, or whatever the case may be. Okay, so be that critical reader from here on out, and call them on it if you notice it.